Hello, everybody. So, we're going to get into the lungs, the respiratory system, and we're going to talk a little bit about first the mechanics of it. Then we're going to get into other things related to it, like surface tension, surfactant, and how those assist within like the alveoli of the cell or in the lungs. And then we're also going to talk about some issues that may occur. Um, if we see some struggles with our lungs here we'll just scroll up. We'll talk about compliance and elastance as well. I said surface tension, and then we'll talk about partial pressure and solubilities. In the next cut, because I just want to make sure I teach that good and study up on it a little more. Nevertheless, let's get into it. So right here we have the lungs. Let's get into a little bit of the um, anatomy of it. Anatomy is the word for it. So what are we looking at here? So right here, you can see, oh, that's sort of my little red thing. Right here, we can see these lungs here. The technical name for these are called the visceral pleura. And then in the green here, we have this other area in which where our lungs like to hang out in. It's the sac also filled with air um, that our lungs sit in. Um, and this is called the parietal pleura. The parietal pleura. And then we have the space in the parietal pleura that is between the edge of the parietal pleura and the visceral pleura. We call that the pleural split space. We have the diaphragm down here, and then we have like our ribs and our chest wall is what we call it usually. So let's get into it a little deeper, huh? Why do we breathe? What is the mechanics? What is the physiology behind this? How is it possible, and why is it so important? Well, let's get into it. So let's just make one thing known. The atmospheric pressure, which we'll see it abbreviated as such, pressure of the atmosphere, is 760 milli millimeters of mercury. Okay. This is, we're going to see, is referred to as zero. 760 is the baseline of the lungs. So let's just fix this real quick. Mercury, right? But that's just pretty much standard. So we're going to see understand that it's at 760, but that's typically zero. As we get into the as we get into the lung here, we notice here that I've written the intrapulmonary pressure. Here inside the visceral pleura, we have the intrapulmonary pressure. The lung here is made up of our friends alveoli as well. Let me go back to the lecture notes here, just so I can show you a little bit more of how it's branched. So you see here, our alveoli are these little branches here that branch off. These are the things that are going to inflate in our lungs, really allow that oxygen and CO2 to hit our lungs to allow it to expand. This is where the capillaries are, so we're gonna need the blood and the blood to reach there so it can allow it to inflate and then receive oxygen and all the other important things that our body needs. Okay, so alveoli, please pardon the what is it called? The typos or the misspelling. So generally here, let's go back to our intrapulmonary pressure. We have 760 in our lungs as well. Why is that? It's just going to match the atmospheric pressure. It's always just going to be our baseline, and we're looking at rest right here. We're not inhaling nor exhaling. How is that possible? I'm not sure, but let's just say we're at rest, right? We're just completely neutral. It's going to match the atmospheric pressure. So what do we say that equals 0 or 760 millimeters of mercury? Our intrapleural space is a little different. We are negative pressure breathers. That means for us to breathe in, we don't have something pushing that air in. It more so needs to get sucked in, or the space needs to be made available for us to breathe in, right? So we notice here in our intrapleural pressure that we are at -4. And what does that mean? That means we are at a deficit of pressure here. We have to understand that pressure moves from high to low, right? Like our concentration gradients that we've learned. Um, so we're going to see that our alveoli and our lungs are going to expand and fill this space, allowing us to breathe. Okay, let's get into it a little more. There are three important things to understand about the intrapleural pressure. It's made up of the elasticity of the lungs, surface tension, and the elasticity of the chest wall. We're not going to talk much about the chest wall. We talked a little bit about it in lecture, uh, but we're not. It's not super important. Surface tension is important, and elasticity is super important. So just understand as the thoracic cavity volume increases, the intrapleural pressure decreases. So our diaphragm is going to drop, our chest is going to expand, and that's going to lead to more volume forming, which is going to decrease pressure, right? Because we know that if P1 and V1 equals P2 and V2, and pressure decreases, or pressure decreases, that means our volume is increasing because there's more space to be had, correct? Correct. All right, let's move on. Next, here's some a little more mechanics. Let's talk about um, breathing in and out, right? What is it called? Um, when we breathe in, our diaphragm is contracting. Oh my gosh, that's gonna bug me. Let me look at it because let's see here. Let's see here. Where's my chat GPT? Where's my chat GPT? Because I just asked it some clarifying questions. Inspiration is breathing in, expiration is breathing out. Thank you. Thank you, chat. Okay, so diaphragm is contracting, which causes the diaphragm to move down. So what does that do? That increases the volume of that interst or that pleural space, right? But parietal pleural is going to move down. We're going to have more space to be had, which is going to decrease the pressure in the lungs and the pleural space, right? So we're going to be able to see that our pressure, intrapulmonary pressure is going to go down to -1. Once our intrapulmonary pressure moves down to 1, that means the air is going to want to come in because what happens? We go from high to low, right? So intrapleural pressure will then drop, right? Due to the volume increasing in the pleural split, in the pleural space, that's going to get moved down because our um, diaphragm is moving down. So this helps lengthen the lungs, allow more split space for the lungs to inflate, thanks to the diaphragm. When we, uh, in expiration, right, breathing out, we see more, we see the opposite happen, right? Like I talked about, positive pressure is going to want to force things out rather than create space for things to come in as we see in negative pressure. So what happens? Our lungs fill with air. Therefore, that pressure rushed in earlier. Now that it's filled, it's going to want to push that stuff out, baby. So it's going to push it out. And those are the mechanics of breathing. Let's go up to surface tension, surfactants, and just compliance and elastance. So let's break it down. Compliance is the at which the, is the ease in which our lungs are able to stretch, and which something is able to stretch. So we think of our lungs, our chest wall. That's just them moving outwards, right? We're thinking of them moving outwards and allowing that stretch to take place. That is represented by volume over pressure, right? Because volume is increasing as we move out. And the opposite, not the well, the other factor we're going to look into is elasticity, is the resistance to stretch, right? Elastance is the power and the strength in which something wants to go back to normal, right? If we have a rubber band here and we're pulling it out, it really wants to go back in even more forcefully. That's what we see here. It's the resistance to stretch. Like our heart earlier, we knew that it didn't want to stretch out, but that return of it is super important for contracting and pushing out blood. It's the same thing for the lungs, but with air. So this is measured by pressure over volume. So there's three things that really help with defining compliance. It's the elasticity of the lungs, surface tension, and the elasticity of the chest wall. So how are the elasticities going to uh, affect our compliance, right? Because they're inversely correlated. One wants to stretch out, one wants to stretch back into its normal shape. So lungs are built to be generally very compliant. But also just the right amount of elasticity. If we have too much of one or the other, we could really have uh, issues. So that's why we want them to be the same at all times, or an equal opposing force, right? So we could just be normal and breathe our air. So let's go into some things that kind of were talked about in lecture. We have pulmonary fibrosis, right? Pulmonary fibrosis is going to cause a lot of scar tissue to be had in the lungs. What does that do? If we have a lot of scar tissue, it's not the same stretchy muscle or skin, right, or tissue that we have. It's going to increase in stiffness, which is going to increase elasticity and decrease compliance. What next? We have emphysema. Emphysema is a scary one because here in our alveoli, we have these little branches, as you can see here in the normal one. That lining in there is slowly going to get eaten up and it's going to smooth out like so. We're not going to have those little bubbles that we can fill up like before. So, in turn, we lose elasticity, right? Where we don't have as much structure. We're smoothing out and we're able to stretch more easily. Or we're not able to retract as easily. This is kind of big in emphysema because we see that people have an easy time breathing in, but they have a hard time breathing out due to that decreased elasticity and increased compliance. Okay, let's get into surface tension. Surface tension is the water layer in our alveoli that interacts with the air. It works really hard to constrict the alveoli. It wants the alveoli to collapse, right? To shrink, to move inwards like so. So, as you can see here, when we increase surface tension, we have a decreased compliance. So if we have a decreased compliance, it's gonna be harder to what? Breathe in. So that means it's gonna require a lot more work. And then you see here, vice versa. Here's some examples that we'll kind of skip over that kind of relate to how compliance is affected by certain diseases. So you guys could read over that. Then we'll get into surface tension. Surface tension is super cool. I really enjoyed learning this and its relation with surfactants. So, like I talked about a little bit before, surface tension is the relationship between air and water in the alveoli. The whole goal of this surface tension of these hydrogen bonds formed between these water molecules is to thin out and cause the collapsing of the alveoli, right? Moving it in like we drew here. So as the water layer thins, the alveoli collapses and pushes the air out, right? So that constriction can be a very good thing, but right in moderation. It has to be perfectly balanced. So we'll get into how surfactants help with that in a little bit. Let's break down um, the the layer here though. So we have type 1 and type 2 alveolar cells. So these are cells on the surface here. As you can see, we're going to have our water layer and our gas layer up here. Type 1 assists a ton with gas exchange, right? So it's going to allow oxygen and CO2 to be moved, nitrogen to be moved in and out of the cell in the right way that our body needs, right? And our type 2 cells are the ones that produce surfactant. So what is surfactant? Surfactant is made up of 90% lipids and 10% proteins. And the gestational phase when we're in pregnancy, at 24 weeks, our cortisol starts stimulating the production of surfactant, right? It's going to stimulate those type 2 alveolar cells. We have two different kinds, or two different important parts of the surfactants. We have the dipomidyl part of it, which are these two fatty acid chains. We have the phosphatidyl, which is choline, which is the hydrophilic part, and then we have the hydrophobic part, which is the fatty acid chains. These attach on the surface of the water layer and begin to pull it back up, right? So it's going to be that resisting force in surface tension. It's not going to allow it to completely allow the alveoli to collapse. It's going to be our saving grace and pull our water layer up so we don't completely collapse our alveoli and collapse our lungs, right? So those are super important. So surfactants will pull water away. So this decreases the surface tension, right? Let's go into our little uh, equation here. What was it called? It's called Laplace's law. It's described as the collapsing pressure, right? And it's defined as 2, a constant, times T, our surface tension, divided by our radius. As the tension goes up, the surface tension goes up, what happens? Our pressure will go up. And as it goes down, our pressure will go down. The more important thing is how it will affect, how the radius will affect this. If we have like a mucus building up there, we're gonna get our alveoli is gonna become hypoventilated, right? It's not gonna get enough air, which then in turn is gonna cause it to get smaller, right? Because we have not enough airflow going in, which is just not gonna allow it to inflate as much. When the radius is smaller, what does that mean? That just means we're gonna have an increase of pressure. Okay, I'm gonna take a little break here and blow my nose, get into the shower so I can feel better. And then we're going to tackle the partial pressure and solubilities and some other fun stuff. All right, be right back. All right, let's knock this out in about 5 minutes so I can upload this video. Partial pressure and solubilities. Okay, remember high concentration and low. All right, just remember that. So our partial pressure of oxygen inspiration is 160. Once it gets into the alveoli, it's 104. CO2 in the alveoli is 40 millimeters per mercury. What does that mean? Since CO2 is low, and it's higher in the blood vessel, it's going to cross. And O2 is going to cross because since it's so high in the alveoli and low in the blood, we need it to get in the blood because oxygen is life. Okay. Then when we our right ventricles through the pulmonary arteries is pushing in the CO2 that we then need to get rid of, right? We then have hemoglobin within the red blood cells. The red blood cells are going to be attached to the CO2. We can have deoxygenated blood, which is just blood that is not oxygenated. This is known as the T state. Let's find it here. The T state is deoxygenated, which means it's tugged. So it's ready um, to get pulled down, um, which means it's get ready to get pulled down for oxygen to be attached. So it's just waiting for the oxygen. Our state is when it is oxygenated, it's relaxed. So CO2 will trigger the T state to form. Okay. So we have our 2,3-B BG helps hemoglobin get to the T state as well. Okay. Wonderful. So it'll attach to our hemoglobin, oxygen will attach to our hemoglobin, and we'll see shifts happen when that occurs. Oxygen will then, the partial oxygen pressure will then increase to 98 to 100, and our carbon dioxide to 40, right? Okay, good. Then we'll have bicarbonate in the blood, which will then need to be shifted and broken down into carbon dioxide to get moved throughout the blood. We also have conformational shifts of chloride getting into the blood to allow bicarbonate to get into the blood, then removed to form more carbon dioxide, then to leave the cell. CO2 is very soluble in the blood, so it'll get shot out. The more it's hard how the effect is the hemoglobin's affinity for oxygen switches. So it's hard for oxygen to attach at first, but once the oxygen piles on, it gets easier. For example, one is the hardest to attach oxygen to. For the fourth one that is attached can it be attached on easily because the affinity increases. The oxygens will bond to the irons um, within the red blood, the hemoglobin. Okay, cool. Now let's quickly fill in some gaps. Let's talk about the alveolar gas equation. So the equation goes as follows. Okay, so yes, it goes as follow. So first we can look here. We know that the BaO2 is the alveolar partial pressure of oxygen. FiO2, right? The next one is the fraction of inspired oxygen. PATM is the atmospheric pressure. PH2O is the water vapor pressure in the airways. PaCO2 is the arterial CO2 partial pressure. Cool. So, how would this be useful in clinicals? So, we need to understand our oxygen efficiency. So, by calculating PaO2, we can compare the gas of the blood. So, it really helps us identify like hypoxemia and stuff like that. So, it gives us a good, good indication of where our oxygen's at, how much is in there, and whether like perhaps the pressure of water or the pressure of CO2 and our ratios are all correct. Okay. So that's super important as well. Okay. And that should conclude our video for today. To talk about the curve. How do we pull that up? You guys hear me all right? Okay. Now let's talk about what the frick it is. Let's talk about the oxygen hemoglobin dissociation curve and how all that stuff is important to it, or why it is. And yeah, let's just talk about the importance of it now. The curves are S-shaped and on a straight line. This is pretty important. Why? So, because hemoglobin is going to change its shape when oxygen binds. The first oxygen, like we talked about, is hard to bind, but it gets easier as the time goes on. It gets steep due to the drop of oxygen. So, so the saturation drops. So that means the tissues are getting a ton of oxygen, and we need it like when we're exercising. So we can kind of see that, for example, um, in the middle, right? We can see that in the middle that we are perfectly fine there. So then when it flattens out, that means there's another there's a huge change in partial alveolar pressure of oxygen because there's small changes in the saturation. That means the lungs can reabsorb that oxygen easily, right? Because we need that to flatten out so our oxygen can um, improve. So when our curves are shifted to the right, like the red, what are the causes of this? Increased CO2, acidity, or maybe even temperature. So we can see this happen in um, fever or exercise. We see an increase of 2/3 BPG. So yeah, and then with the left side curve, we have a decrease of all the other things, right? Decrease of CO2, um, acidity, temperature, 2/3 BPG. This could be caused by alkalosis, right? It's seen a lot in hypothermia and fetal hemoglobin syndrome. And obviously the middle is just normal. All right, thanks guys.